Well, thanks for having me back. This is my second time here, so thanks for this. And I'm here representing Sipwise. You may know us from what you may call our flagship product, usually called NGCP. I'm sure some of you are familiar with that already. If you don't know it, it's a Class 5 soft switch appliance. It's fully open source. There's a free community edition you can download. So if you don't know it, go ahead and check it out. There's some good stuff in there. One of the components of NGCP is RTP engine. And some of you are probably using RTP engine as a kind of a standalone product. And that's why I'm here today, because RTP engine is mainly my doing, for which I can only apologize. And there's a few use cases, as Fred already touched upon, for RTP engine. The main one is probably as a media proxy, just to solve NAT issues, for example, or just to anchor your media, or you want to do media forking, things like that. But the other use case is for transcoding. So we support a fair number of codecs. And I know there's some fairly large installations out there that use RTP engine quite heavily for transcoding, which is good, I guess. And if you know me, if you know RTP engine, we're always concerned about performance. And for the media proxy use case, we have that covered. We have a kernel module. You can push a lot of media, a lot of traffic very easily, very quickly. With very little overhead. You can do thousands of calls on one machine, even tens of thousands of calls if you want, in some cases. Not a problem. But with transcoding, things are looking a bit different. Now, that is not to say that we have bad performance, but the thing is that when you're transcoding, you're kind of at the mercy of the codec. You're going to use a library of some sort that does the codec. And if the codec performs badly, then that's just what you get, and you have to live with it. There's not much you can do. And for some codecs, your choice of library, maybe just one, maybe two. So this is kind of a tricky situation if you have bad performance with transcoding, because you're kind of stuck. And this is the segue to the main topic for today, which is GPUs. And if you can put two and two together, you can kind of guess where this is going. So GPUs, traditionally, of course, everybody knows it, have been used for graphics processing. The clue is in the name. That means 3D rendering, other general visual effects, like you would find on a desktop UI, for example, blurring, transparency, that kind of stuff. Also useful, GPUs are for video encoding and decoding, sometimes called hardware-accelerated video encoding, decoding. Still graphics related, of course, but this is now more on the computing side of things, and this is where it kind of gets interesting. There's a few different implementations out there. NVIDIA has NVEnc, that's kind of popular. AMD has VCE for their GPUs. Even Intel has an implementation for their chips. They call it QuickSync. And then there's some other use cases for, of course, AI. Everybody is doing AI these days. ChatGPT, DALL-E, all those fun things, they would be impossible without GPUs. And then there's some more obscure use cases for GPUs, like password cracking or Bitcoin mining, which is kind of the same thing. So there's quite a variety of use cases here, but where is audio in all this? Where is the audio equivalent of NVEnc, for example? We looked for it, and basically found very little. It doesn't seem to exist. So there are some audio toolkits out there from NVIDIA, for example, for certain specific use cases, but nothing useful for what we wanted to do. There's some proof of concept research papers out there that are not really usable. There is one commercial SBC that I know of that says they support transcoding on GPUs, but it's kind of limited. You kind of get to choose one codec combination that you want to run on the GPU, and they only support certain very expensive GPUs. So also not a good option for what we were looking for. And as it turns out, there is a reason why this is not commonly done, and I'll try to explain this. So let's look at how those GPUs are working. If you're doing GPU programming, you basically have a choice between CUDA and OpenCL. OpenCL is, of course, the open programming language for this kind of stuff. It supports a variety of hardware. And the alternative is CUDA, which is NVIDIA specific. Now, we decided to go with CUDA, and that is not because NVIDIA are such champions of open source software. Unfortunately, quite the opposite is the case. Linus Torvalds famously had some words to say about this, 2 words in particular that start with F and end with U. But the fact is that CUDA has something like 90% market share in this general purpose GPU programming. And if you do a side-by-side comparison in terms of performance, CUDA still has an edge. So that was a logical choice for us. If you're looking at the specs for a graphics card, an NVIDIA graphics cards, you're going to find the number of CUDA cores listed as a kind of a performance indicator. And we can have a kind of a quick look at that here, if that is readable. So on this laptop here, I have 5,000 CUDA cores. That kind of sounds impressive, right? Now, what does that mean? Does it mean I can have 5,000 instructions executing here at the same time? Does that mean I can have 5,000 threads running at the same time? Who thinks that that's what that means? Who thinks that's accurate? No, nobody willing to stick their neck out? Well, if you think that's what that means, you would actually be correct, but you would also be completely wrong. So I'll try to explain. What the GPUs employ is what's called a SIMT architecture. And this is, what does SIMT mean? It basically means that NVIDIA is terrible at naming things. You may know SIMD, which is single instruction, multiple data. And that kind of makes sense. SIMT, on the other hand, means single instruction, multiple threads. And I remember the first time I was reading about SIMT, it didn't make any sense to me. So I kept reading about it, and after about the 20th time of reading about it, it still didn't make sense to me. So again, I'll try to explain. The important part about the GPUs is that these cores, the CUDA cores, they exist in groups. And this is not some artificial limitation that CUDA or the software puts on you, but this is how the hardware is built. It's wired that way. And there's multiple levels of these groupings. And depending on which level you're looking at which grouping you're looking at, the cores are sharing certain hardware amongst themselves. And the smallest of these groupings is what NVIDIA calls a warp. Again, NVIDIA being terrible at naming things, because what the hell is a warp? Are we talking about warp speed here? Are these warp cores? OpenCL actually calls this an execution unit, I think, which actually makes sense. So what this means is that a warp is 32 cores. They exist in a group. And these 32 cores can, in fact, execute 32 instructions at the same time, but only if it's the same instruction. If 32 threads on those 32 cores try to do different things, you get what the next slide is going to talk about. I'll get to that in a second. Another thing is CUDA cores are sharing are registers. That's right, CUDA cores do not have their own registers like CPU cores do. Instead, the registers, they're held in the multiprocessor. It's a higher level structure, and they're given out to CUDA cores on demand as they need them. And it is actually possible to run out of registers. Now, there are hundreds of registers, yeah, but you can still run out. And when that happens, your code does not execute. But going back to the warps, because that is the most important part here, what happens is, I try to visualize this with just 2 threads and 2 cores. If you have those 2 threads both trying to do an addition at the same time, then those 2 instructions will actually execute at the same time. But if you have those 2 threads now wanting to do a different instruction, for example, one wants to do a move, the other one wants to do a subtraction, what happens is the first core does its instruction, while the other core has to sleep. And in the next cycle, the second core gets to do its instruction, while the first core has to sleep. And then if they converge again, they want to do the same instruction again, they can do it at the same time again. Now imagine if you had not just 2 threads and 2 cores, but 32 of them, and they all try to do different things. Things would come to a crawl. Ask me how I know this. And the problem with CUDA is that it does not help you there. It's completely up to you to make sure that your code does not do this. So how can you work with this to achieve high-speed transcoding on a GPU? Well, you do have to do it codec specific. You have to cater to how the codec works. And I picked a few examples there, starting with G711, which is kind of a joke, because it barely qualifies as a codec. This is the entire codec. This is all of G711. It looks a bit daunting because it's a kind of a mathematical representation. But in reality, this is implemented as a lookup table, because that's all you need. And with a lookup table, lookup tables are very fast. So when you do it on a CPU, you have to consider, is it actually worth it offloading this to the GPU? Because every time you do it on the GPU, there's an overhead involved. You have to push the data across the bus, you have to launch the kernel, and so on. So there's a penalty involved. So unless you have a large amount of data to transcode, it might not even worth it to do it on the GPU. Then I picked G722 as a kind of an in-between. G722 still does sample-by-sample encoding, like G711 does. But there's actually an encoder state, which is updated with each sample. And then this encoder state is used to do a kind of a prediction to achieve better compression. Now, this is not good news for GPUs, because this is not easily parallelizable, because you have to go sample by sample. This is sequential, so you cannot really do it in parallel easily. The good news is that the encoding process for G722 is very linear. So you can be very sure that if you have multiple encoders working on multiple frames, they all actually do the same thing. So a logical choice would be to just dedicate one thread to one encoder and just have them do their thing, and you will know your threads will not diverge. And this actually works. There's only one problem with memory access, because one warp can make one memory access at a time, but there are solutions to this too. Now let's talk about Opus. Now Opus is the big kahuna here, because Opus is extremely complex codec. In fact, it's not just one codec, it's 2 of them, Silk and Celt, that have kind of been merged. There's multiple encoding modes in Opus. Depending on the encoding mode, one codec might be used, or the other one might be used, or both of them might be used in a kind of a hybrid mode. There's different bit rates, there's single channel, dual channel, there's multiple sampling rates supported. There's different frame sizes you can choose from. There's a lot of heavy lifting involved in Opus. There's multiple predictive models in there. So it's extremely complex codec. And the bottom line is that it's virtually impossible to avoid that your threads diverge. So how can you do this on the GPU anyway? And one solution is to take a group of threads matching the warp, so 32 threads, dedicated to one encoder, and have all those threads work together to do the encoding process. And then you do within those 32 threads, within that block, kind of a SIMD-like approach to kind of try to accelerate it and parallelize it within the thread block. Now for the actual implementation, how to make this work. For comparison, this is how you would do it, just plain transcoding on a CPU. Basically, each thread does it in a loop, gets a frame from the network, decodes it, encodes it, sends it back out, and then starts over. And each thread is kind of on its own, it's independent, and they don't interfere. Now, when you're invoking the GPU, there's two approaches you can take. This is the asynchronous approach, which is actually very similar to the CPU implementation. So this is quite easy to implement, where each thread, now these are CPU threads, each thread receives a packet, a frame from the network, adds it to a queue for the GPU to process, and then waits. It just waits until the result is ready. And then there's a dedicated thread that just collects and collects and collects until it has enough, and then activates the GPU, does the actual transcoding, and then returns the results to the threads that are waiting, and then those threads are sending out the result. The disadvantage is that this requires a lot of threads. And I will give you a demo in just a minute. The other option is to do it asynchronously, where each thread just gets a frame in, adds it to the queue, and then continues to receive frames and queue them up, while the GPU thread collects and collects and collects, then invokes the GPU, and then fires a kind of a callback to actually send the results out. This requires not as many threads, but the disadvantage is that then you have to deal with maybe deadlocks, reference counts, other issues with this kind of setup. So it might perform better, but it's more difficult to implement. And now my contribution to the dangerous demos, because we can actually look at what this looks like in real life. So this is brand new. This is from RTP engine, but it's not on GitHub yet. It's kind of a performance testing tool / simulator. So this is using the internal tool chain from RTP engine to simulate a transcoding scenario. And it plots out the CPU usage and so on. So this is a regular transcoding on the CPU. And we can just add one stream. So this does PCMA to Opus transcoding. And this is just one thread, and right now one call is running. And you can see a bit of CPU usage there. And if you increase the number of calls here, let's go to 10, you can see that CPU usage is getting there already. And you can crank it up to, let's say, 50 of those streams, 50 streams, 50% CPU. Now, this is single thread only, of course. I have more CPU cores here, not a problem. So you just add more threads. And it kind of balances out. And let's say you put it, you give it 8 threads, and you can crank it up to, let's say, I don't know, 350 streams, 450, 550, and then you get to about 50% CPU. So this is expected. This is nothing unusual. The other view I have here in this testing tool is the real-time usage. So the first one, this is CPU usage. And the other one is the real-time usage, which is just how much time it actually takes. And as expected, it's about the same, right? So I can switch back and forth between the two, and they look the same. So this is plain old transcoding on the CPU, nothing new here. But I can activate the GPU transcoding now, because we have this implemented. And starting again with a single thread, and I'm adding 1 call as before. And CPU usage, not much happening. But if I switch over to the real-time usage, you can see there's already considerable time spent here just on 1 stream. And this is just the overhead that is needed to activate the GPU, push the data, launch the kernel, get the result back, and so on. Now, if I add a few more calls here, let's say this is just 3 calls now, and it's already using about 50% of the real time to do those 3. This is the synchronous approach that I just mentioned earlier. So these happen one after the other because I just have 1 thread. So I do 1 encoding, it has to wait, and then does the second one. If I look at the CPU usage, there's barely anything there, of course. But, and this is where it gets dangerous, because this might set the podium on fire. If I actually want to make use of the parallelism, I have to dramatically increase the number of threads here. And they won't fit on the screen, but let's go with about 500 or so. And then crank up the number of streams. And you can see it's filling in. So I'm here at about 500 streams. And it's fluctuating wildly because of the way these transcoding jobs are bunched together and collected and then done at once. But the point is, it's holding up. I'm at 600 streams now. And I can switch over to the CPU usage. There's nothing there. But the real-time usage, you can see it there. And keep in mind, this is a consumer-grade, off-the-shelf laptop with a mobile GPU in it running on battery. So this is clocked down. And it can do 600 threads, maybe a bit more. Yeah, OK, that was about the limit. I can do a bit more. All right, that was it. Any questions?
That was an exciting end to a presentation. Daniel's here with a question. Abby, are you head of mics? Excellent. Thank you. And then we'll come to Zoa on the front in a moment.
Thanks. OK. So the question would be about the balance between the cost. OK, most of some boxes or laptops or whatever systems come with the GPUs, but when would it be like buying more hardware to increase transcoding, knowing that the GPUs are also not that cheap?
Yeah, that's a good question. And the price range for the GPUs, it varies wildly. And that's why we kind of focused on the consumer-grade GPUs. So I cannot give you a straight answer because GPUs obviously are not free, but then CPUs also are not free. And we want to do kind of a proper performance test with different GPUs, but maybe you know there was a GPU shortage, so we couldn't really do that. And the other thing you can do with this is that you can kind of balance the transcoding between CPU and the GPU. So you can have those 600 running on the GPU plus maybe another 600 on the CPU. And as a follow-up.
Okay, then let me put it from the cost of code complexity. Maintaining, it's any complexity added to maintain the both, to support both of them, and eventually, as you said, you went now for the NVIDIA GPUs, right?
This
in
is
the
NVIDIA
future,
only,
if
yeah.
you come another vendor and you have to add it, it's something that you think could be reused, or it will be like, okay, implement it from scratch and whatever?
So this is specific for NVIDIA for now. We don't have any plans to change it, at least in the near future. The Opus encoder we have, it's actually based on libopus, the actual code that's been ported to CUDA and then kind of parallelized. So it supports everything that regular Opus supports. And maintaining it should not be a problem unless there are major changes. And the GPU transcoding itself, it's going to be bundled into a library. Like, it's not into RTP engine itself, it's kind of a separate library that might be useful for other things as well.
Thank you.
What is the performance like if you would run it on a much faster CPU?
Like I said, we didn't really have a chance to test this because they were difficult to get a hold of.
No, I mean the CPU, not the GPU.
Oh, the CPU?
Yeah.
The transcoding performance?
Does it scale linearly? Like, I don't know how many cores you had on the laptop?
So just for demonstration, this was with 8 threads. So for 8 cores, I actually have 16 here, so you could scale it up. Mm-hmm. I know there's CPUs out there with like 128 cores, but they're very expensive, right? Mm-hmm. So it's a trade-off between cost and performance you get.
Okay, so for the GPU question, if you want to do some testing, just tell me what to test. I think we have a bit of everything, except for the latest generation. I think we have all the GPUs.
Okay, I'll get to it.
Okay, I think that's... oh, actually, was there one more question over there, sir? Or was that just somebody yawning? Okay, I think... Oh, there you go. Oh, goodness me, we've got 2 questions now. So we'll go for Dragos there and then Liv, you at the back.
Hi, so I was wondering if you played with the complexity parameter of the Opus library, and also if you're trying to do encoding on GPU and decoding on CPU or stuff like that. Yeah, so decoding is a lot more lightweight than encoding is, so you don't get as much benefit. But for example, you could combine it Opus to Opus transcoding, for example, right? And then you do both on the GPU. About the complexity, this is supported because, like I said, this is based on libopus, so all the options are supported. On the CPU, it shaves off about 50% of the CPU usage. On the GPU, I haven't tested it, but from looking at the code, it does like loops, so it probably does about the same thing. But I don't know for sure.
Thank you. And we'll just go with Liviu right at the back there. Do you still have a question, Liviu? You do? Okay. Right in the back. Thank you.
Thank you for the presentation, Richard. Just a quick question on hardware, because I understand for CUDA to work, you have to have an NVIDIA card. Yeah. So the question is just what kind of consumer card is it? What model?
This is an RTX 3070, the mobile version of it, on battery, like I said. I tried this plugged in too, it actually performs better. Other ones, like I said, we didn't have a chance to test it, unfortunately.
Okay. It's good to get geeky with the model number, though, isn't it? Excellent. Thank you, Liviu. Let's give Richard a warm round of applause. Thank you, Richard.